Okay, so what we have is notice that this says extending solution.
Mhm.
That means that we start with a solution and make it better. Okay. All right. So let's suppose we have uh, so let's suppose we have a fifth degree polynomial. Actually, that's right here. That's this polynomial down here. So let me just move it up. Oh, okay. Now let me think. Let me be careful here for a second.
Diyebilir.
Let me be careful here for a second.
Okay. Okay, the x value is our estimation by using the cubic formula. So IDFT.
All right. Let me start. Let me start here. Let me backtrack a little bit. Okay. Whoops. Sorry. Okay. Uh, so I can say so far we have a cubic approximation
Mhm.
to p of e I theta um, of r e to I theta, and this is going to be and we have roots. We have roots of this cubic approximation. Right. So we want to do better. Uh, um, yeah, that's right. So let me think about this for a second. So what we have is we have midpoint. I think we're calling midpoint phi. The midpoint of the interval is called phi, I think. And then we have the we have the approximate. We found the so what we found was the so and uh, we have we have okay. So I'm going to call this I think we're calling this f.
Mhm.
Is that what we call f? Or oh, here, I'm sorry. We want the imaginary part, not just
Yes,
p.
yes.
Sorry.
Yes.
So let me make that imaginary part. So this is what we're defining as f of theta. Okay. So we have a midpoint phi, and we have f of phi. We have prime of phi. We have f double prime of phi, and we have f triple prime of phi. This is what we already have. So far what I'm doing is just repeating. All right, this is what we already have, and then we can use. So we're using the Taylor approximation. if I take f of phi plus some small number, that's approximately equal to f of phi plus f prime of phi times h plus f double prime of phi times h squared over 2 plus f triple prime of phi h cubed over 6. This is just the same as what you've been doing here. This
just the Taylor.
you see f prime, f double prime, f triple prime. So this x here is really what you're this x here is really finding h. So why don't I just say we want to start here? This is just reference. And this agrees with the code. But in your write-up, you should start here. Let's see. Actually, this part we don't even need. I'll just take this out. Right. And maybe if to be consistent, I can go ahead and call this h. Let's see. All right. Yeah. Let me make this. Let me make this a little bit more clear. I might as well rewrite this now while I'm doing it. Okay. Yeah. Why don't I just make this a little more clear? Okay, here, I think I'll just rearrange this. In fact, and if you want a reference, you can look at this here. I'm going to take this out, and I think I'll just start over. That's not working. Yeah, I'll just start over. Actually, why don't I just go ahead and put that here, because this is just what we're... Okay. I'll just take this and move it over. Okay, so, all right, so far we have a cubic approximation to this, okay, so let me just say this. So far, so we have the midpoint phi, and we have this. We have the midpoint phi, and we have these values. So we're going to use the Taylor approximation. Now what we want to do is we want to find h that's a root, that makes a root. So we want to find roots of f. So we want to find h such that f of v plus h is equal to 0. Right? Now, here's your f of v plus h, right?
Mm-hmm.
So this is a cubic equation. It's a cubic equation in H. All right. In fact, that's the cubic equation that we have. But instead of solving the equation directly, so instead of solving directly, for H, we modify the equation and solve for 1 over H, which is the largest, and which is going to be the largest root. Since H is small. And if you want to see this in the code, this is also reflected in the code.
Mm-hmm.
If you look there, I'll pull up.
Remember, there might be some dividing by 0 issues.
Yes, that's right.
That's why we use.
Yes, that's right. We use this. So I'll just refer you to which line in the code this is talking about.
So I think find it. It's about non-zero roots.
Let's see.
Okay, it is computing PQR. We divide.
Yeah. Well, yeah. That it is there. Let's see if I can find it.
97 per 99.
I even forget what the name of this file is. Is it cubic Newton or what is it?
This define cubic coefficients.
I mean, what's the name of the file? I don't remember.
It is cubic Newton 2.
Cubic Newton 2. All right. Okay, so I opened the wrong one. Okay, so down here, yeah, this one, so this is line starting with line 90. In the code. Okay. Okay, so now once we find H, then we have, since H is a root, then we have this is equal to, then we have this is equal to 0. We have f of phi. Well, we have f of v plus h is approximately equal to 0. Or, so I can say, so we have f of phi plus f prime of phi times h plus f double prime of phi times h squared over 2 plus f triple prime of phi times h cubed over 6. We have this equal to 0 because h is a root. And so this means that f of phi plus h is approximately equal to 0. Or we can say up to third order. if you only take the first 4 terms of the Taylor series, then it agrees, and I have a root. But of course, this function has more terms. Okay, so h is not actually a root of f, but it should be close to a root. So we want to improve our estimate of the root. Because h is only accurate up to 3rd order. Okay. All right. So does that make sense?
Yes.
All right. So let's add 2 more terms.
It is like Taylor polynomial approximation, right? If we include more terms, it's going to be more accurate.
Yes, 2 more terms.
And I just need to add plus f to the 4th.
All right.
Theta to the 4th over 24.
So let's do this. So we have, oh, what's that down there? That's funny. Let me get rid of it.
It is
Something left over from before.
This is something we discussed at the very beginning, like in September.
All right, so let's see. So we add 2 more terms to the approximation. Okay, so now instead of just having, but you see, we still have to do that calculation. We're not going to replace that calculation. We're going to do an additional calculation. So we have f of theta plus h is equal to f of theta plus f prime of theta h plus f double prime of theta times h squared over 2 plus f triple prime of theta times h cubed over 6, and then plus f4 theta h to the 4 over what is it, 24. Okay. All right, we can do, well, I think I'm just going to do 1 term because it actually works the same for higher terms. We'll just do, well, I did say 2 more terms, so we'll go ahead and do 2 more terms. And then that's going to be 120. All right. So you can see when h is small, these terms will be small because of the 24 and the 120. But if h is big, then it will be more significant. Now we know we have chosen h such that we've already chosen h such that the first 4 terms give 0. Right? That's up here. You see? We've already chosen h to be a root of those terms. You have this here, and those are these terms here. Okay. So this here is 0. So this here is also 0. Those terms are 0. This should be approximate here. It's not exactly. So f of theta plus h is not 0. It's equal to these 2 values. Right. So I want to add a correction. Okay. So what I'm going to do is I will do a Taylor expansion. So I want to find a correction. F of theta plus h, I'm sorry, I'll call the correction, I don't know, I suppose I can call it h prime. Or let me just call it k or something. Such that f of theta plus h plus k is equal to 0 to fifth order. Right? F of theta plus a is 0 up to third order. So I want to add two more orders. So if you want to draw a picture here, here's my theta, my h will be here, and my actual root is somewhere over here.
Mm-hmm.
So I want to, I'm sorry, this is theta plus h. This is not h, it's theta plus h.
And we are going to find a k value, it's going to be more closer.
And then this will be theta plus h plus k. Right? And so this will be, it won't be exact, but it will be closer. Right? So this distance is h, and this distance is k. So what I'm going to do is I'm going to do a third order approximation. So I'm going to do it, so I will do a third order Taylor approximation. But not at theta. I'm going to do the approximation at theta plus h. Not at theta. So what I have is that f of theta plus h plus k is approximately equal to f of theta plus h plus f prime of theta plus h times k plus f double prime of theta plus h times k squared over 2, and then plus f triple prime of theta plus h times k cubed over 6. So I will find k.
Okay, yeah, I think I understand, Dr. Throm.
Mm-hmm.
F theta plus h plus k is the fourth degree Taylor polynomial. Right? And
Well, not really. But the point is that it's still a third degree. It's still a third degree polynomial.
The solution theta plus h plus k is our fourth degree Taylor polynomial estimation.
Well, it won't be. Not
Okay.
quite. But the point is that if my Taylor point is closer to the actual value, then the approximation will be more accurate.
And how did we get k? Isn't it with fourth degree Taylor polynomial?
No, we haven't found. We're about to find k.
Ah, okay, we are going to find k.
Okay.
I see.
So I will say that this will be a more accurate estimation than the other one. Because the Taylor approximation is more accurate for smaller values because k is going to be less than h, and the Taylor approximation is more accurate for smaller values. Okay, for values close to the expansion point. Okay, if I have a point here and I do Taylor, if I have a point here and I do some Taylor, and here's my actual function. My Taylor approximation will be very close here. It will be exactly correct here. but it becomes more and more inaccurate the farther away I go. It's quite accurate close to the point, but less and less accurate as you go far away. So you see that the Taylor approximation is more accurate for smaller values. And since I'm still doing a third order Taylor, but since I have smaller values, it's going to be more accurate. So I guess this is kind of an aside. So let's say, all right. So to find k, I need to estimate the coefficients. And what are the coefficients? The coefficients are these here. These coefficients, this one, this one, this one, and this one. Once I find these coefficients, I can find k the same way that I found h. I know, but I'm going to use this fifth order approximation to do that. All right, so let me grab this. Sorry, let me move it over a little bit. And let me clean this up a little bit. I think actually I can do this. Move it a little closer. And move this up. I probably should leave it down there, but I guess it's okay. Okay, and let me clean this up a little bit. All right. So now this is f of theta plus h. Okay. Now remember what I said before is that we chose h so that these values are 0. Okay. So what I have is f of theta plus h is just equal to f4 of theta times h to the fourth over 24 plus f5 of theta times h to the fifth over 120. All right, now I need to find f prime of theta plus h. So what I need to do is I need to take the derivative of this with respect to h. And evaluate when h equals 0. Wait a moment. Let me see here. I need to be careful about this. Let me be careful about this. Because it's not h equals 0. It's not h equals 0, sorry. It's just this, because h has a value. All right. So you tell me, what do I write? What is df of theta plus h dh? What do I get?
So that's going to be, isn't it gonna be h plus f prime theta times h? We will just ignore the last term. Isn't it the fourth degree Taylor polynomial?
No, here I've got this. I have this polynomial in h, and I need to take the derivative with respect to h.
Oh, okay. So it is right here. So h to the fourth over 24, and when I take the derivative, it's going to be h cubed over 6. F to the fourth.
I know the point. I see you're neglecting these terms. You have to include these terms because the value is 0, but the derivative is not 0.
Ah, I understand. So the derivative is not 0.
Yes.
And this is going to be f prime theta.
Yes.
Plus f double prime theta times h.
Yes.
Plus f triple prime theta times h squared over 2.
Yes.
F to the fourth theta h cubed over 6 plus f to the 5 theta h to the 4 over 24.
Okay, good. All right. So that's something that we would have to find. Then we need to find f double prime.
F double prime will be, it's going to be f double prime theta plus f triple prime theta times h. Okay, now it's going to be a cubic. This plus f to the fourth theta h squared over 2 plus f to the fifth theta h cubed over 6.
Okay, and then we need to find the third derivative.
Third derivative will be f triple prime theta plus f to the fourth theta h plus f to the fifth theta h squared over 2.
Okay. All right, now you mentioned that this was a cubic. That really doesn't matter because h is known. We're not going to be solving this. H is known.
Oh.
These are the coefficients that I need. These are exactly the coefficients I need to estimate this, to get this polynomial in K.
Mm-hmm.
So you see f of theta plus h, f prime of theta plus h, f double prime of theta plus h, f triple prime of theta plus h. Those are exactly the coefficients I need. Right, f of theta plus h, f prime, f double prime, and f triple prime. And I can evaluate all of these because I know h. So using these four coefficients, I can estimate k as the root of, well, what was it? I think it was f of theta plus h plus k, f prime of theta plus h, plus, I wrote it on the other side, k squared is the same thing, plus k cubed over 6, times f triple prime of theta plus h. And, okay, in exactly the same way, I found h. You can just duplicate the code. It's the same code. So that means my improved approximation to the root of f is theta plus h plus k. All right, so let's do a recap here. All right, so originally we had our midpoint. We found a Taylor approximation near that midpoint. And we estimated h as the root of this Taylor polynomial. Okay. Now, as I said here, we didn't solve for h directly. We solved for 1 over h. And found that theta plus h is a root up to third order, which has limited accuracy. So we want to improve the accuracy. So what we're going to do is reapproximate, but not around theta plus h. Because we want to find points that, because if we're looking at a close neighborhood of theta plus h, we can give a more accurate approximation. And this is a way that we can add more terms and still use a cubic equation. I can't solve this fifth order equation directly. I don't know how to do that.
Mm-hmm.
But I can, but the thing is that in my code, instead of just computing 3 derivatives, it would be easy for us to add 2 more derivatives. And that's a very easy step. Not a big change.
Yes.
So we've chosen h said the first 4 terms give 0, but these 2 terms don't give 0. So f of x plus h, theta plus h is not 0 to fifth order. It's only 0 to third order.
Mm-hmm.
But we want to find this correction k that makes it 0 to fifth order. So how do we do that? Well, instead of approximating f near theta, we approximate f near theta plus h. So these are the derivatives near theta plus h. But we can evaluate these because we know what h is. We already know what h is. So we're not finding roots to evaluate these. We're just using h to compute them.
Mm-hmm.
So f of theta plus h is easy. This is also not so difficult because we already have these values. We already have all these derivatives at theta. All right, so that's the idea. And once I have these derivatives at theta plus h, I can form another cubic and I can solve this. Now I could do the same process again I could do the same thing I did at theta plus h plus k. I could do it again.
Mm-hmm.
I think I'd like to see how, I think maybe 1 is enough. I think maybe 1 is enough. We can see. If not, we can do it again. But this is a very nice method of getting more than 3 orders by just using cubic equation. Okay, so I'm going to pause here This write-up will need to go in overleaf
Overleaf, okay.
after
So-
the cubic. But remember, we still need the cubic. This is not replacing the cubic.
Okay, so
This
it
is
is
a-
going to be like 2.5, section 2.5.
Something like that. Yes, it's going to be a section after the cubic. So you still need to do the cubic.
I see.
It's not a replacement. It's an enhancement.
And what we can name the new
I don't know, just give it some name. We'll figure out, we can always change.
extending the cubic equation?
Sure,
maybe?
something like that, sure.
And once I write down these, I think I will understand better.
Yeah, I
I
think
kind
in that process of writing you can understand better. Okay. Okay. Now, I guess I didn't say here how to solve it. Here, of course, to solve this, you'll have to use these equations up here. That's what's starting line 90 in the code. So I could say it this way, that this part here this part here is going to be the cubic section. This is talking about the cubic solution. Here, let me put it in a different color. Whoops. I can even... So this all goes in the cubic section. I don't know why I did that. And then solving for h here, of course, this uses these equations here. Oh, sorry, I didn't write the actual equation. The actual equation here is well, I mean, this is to solve a x cubed plus b x squared plus cx plus d equal to 0. And of course, you're going to use 1 over h is going to be your x. Or I should say use x equal 1 over h. And then when you have this, you'll find out that this is going to be your A, this is going to be your B, this is going to be your C, this is going to be your D right there. And then down here, when you do this one, you'll see that, where is it? This is going to be your A, this is going to be your B, this is going to be your C, this is going to be your D. No, I'm sorry, I did it backwards. Sorry. This is going to be your A, B, C, and D. This is A, this is B, this is C, this is C, and then this is D. And you use the same process.